What does it take to keep a lunar base clean and green? As NASA prepares to establish a human presence on and around the moon, reduce, reuse, recycle will become a universal motto, not just an earthly one. Just like on our home planet, future astronauts living on the moon will need to process waste, things like packaging, fabrics, and structural elements. With no garbage trucks or recycling bins, explorers of tomorrow will need innovative solutions to turn their trash into something useful. With limited resources on the moon, astronauts will need to make the most of everything they bring with them, even their garbage. This is where you come in. NASA is calling on inventors, entrepreneurs, students, and visionaries from around the globe to join the LunaRecycle Challenge. The mission? Develop energy-efficient, low-mass, and low-impact recycling technologies. Teams who enter the challenge will compete for a chance to win cash prizes by coming up with novel solutions to transform space waste into usable products to support off-planet science and exploration. Your moon-minded innovations might also revolutionize the way we recycle and handle waste on our own planet, paving the way for sustainable living on the moon and on Earth. Together, let's make one astronaut's trash another's treasure. Every day, we throw away things like food wrappers, plastic, and packaging. And we've developed tools and processes to help us dispose of this trash properly. Off Earth, it's a different story. Without waste management systems in space, even everyday items can become big problems. As we prepare to return astronauts to the moon and eventually onto Mars, one thing is certain: garbage is inevitable and how we handle it matters. But waste is only waste if it is wasted. On the moon, resources are limited. That means astronauts must make the most of everything they bring, even their garbage. In space, trash isn't just waste, it's potential. Imagine an astronaut crew having dinner in a habitat. After the meal, there's now a pile of empty pouches and wrappers headed for the trash. But what if those could be melted down and 3D printed into small tools or components? Or imagine that crew disassembling hardware after landing. What if the leftover brackets and composite panels could be reassembled into a lunar workstation, shelves, or even a rover attachment? And when astronauts change clothes after a long spacewalk, that creates fabric waste. But maybe those old shirts could become insulation panels for a lunar habitat. And the list goes on, from transportation supplies to foam packaging to cargo bags. The possibilities for what to do with them are limitless. But we need your ideas. NASA is calling on inventors, entrepreneurs, researchers, and visionaries from around the globe to join our LunaRecycle Challenge. The mission? Develop energy-efficient, low-mass, and low-impact recycling solutions to transform non-metabolic space trash into usable products to support off-planet science and exploration. Teams who enter the challenge will compete for a chance to win cash prizes. Your ideas could be put into action now as we prepare to return to the moon and beyond.
Hello, and welcome to NASA's LunaRecycle Challenge Winners Announcement. I'm your host, Savannah Bullard, and today we will be announcing the winners of our challenge that innovates trash management and recycling systems for space exploration missions. The idea behind NASA's LunaRecycle Challenge came from the realization that an astronaut generates roughly 125 kilograms of non-metabolic waste in a single month. Non-metabolic waste refers to what we'd consider trash. Think food wrappers, clothing, plastics, metals, and the like. So that's nearly 300 pounds of disposable refuse, all from one person. Managing these outputs is critical. Everything we bring with us to the moon and Mars missions need to be valuable beyond its initial use. This allows us to be more strategic and efficient when planning for long-duration missions, and there's the added benefit of creating a clean and tidy space environment. Today, we'll be hearing from different subject matter experts from the challenge to talk about why this is so important. And we will announce the Phase 1 US and international winners for both the prototype build and digital twin tracks. To kick us off, I would like to introduce Dr. Rajiv Doraiswamy. Rajiv is the Director of Space Technologies and Engineering Research for the College of Engineering at the University of Alabama in Tuscaloosa. Thank you for being here.
Thanks, Savannah. Thanks. I'm really enjoying being here and talking to you today. It's a beautiful day on campus and a great day to announce our winners.
I bet. So, Rajiv, UA has been the allied partner for this challenge since it opened in 2024. Tell me about the partnership and what we've been able to achieve through working together.
Sure. This is UA's first real strategic partnership with the University of Alabama and NASA. Although we have worked with NASA since the inception of the space program, this challenge gives us the opportunity not only to interact with teams from the United States, but all over the world. We're getting a chance to work with inventors, creators, and thinkers from all across the globe, and allowing our subject matter experts and faculty to really expand their reach, which is really the core of the university's mission.
Wonderful. What an
NASA has been
excellent.
a fantastic partner and really looking forward to phase two.
We are too, and we're so glad to be able to work with you in phase two as well. I understand the reception for this challenge was pretty received well, too. Is that right?
It's been fantastic, Savannah. We had over 1,200 registrants from 46 states and over 80 countries, and the judges had their work cut out for them. We had 200 plus viable submissions, and the judges had to work to get that down to our 13 winners and 4 recognized international teams. It's been a lot of work for them, and they've done a fantastic job.
Wow. And I understand that is record breaking for Centennial Challenges to have that well of a reception in a first phase.
It
So
is,
I
and
know
we're really excited about it.
we definitely are too. And thank you for this partnership and for allowing us to get here. And I know you can't disclose much yet, but what are you most looking forward to in phase two?
Well, Savannah, as I looked through the entrance, every time I kept saying to myself, wow, this is a great idea, or wow, I didn't think of that, or wow, I'd really like to see this in action. So we're really looking forward to seeing these fantastic ideas, both on the digital twin and the prototype build side, actually developed into real products. So I think that's going to be really fantastic, not just for us here at UA, but also the community at large. We're really looking forward to welcoming these teams to campus and allowing them an opportunity to show off what they can do, and a time to really interact face to face with our students and our faculty.
Wonderful. Well, I'm certainly excited for it and cannot wait for what's to come. Thank you so much for being with us today, Rajiv.
Thanks again, Savannah.
Of course, now we're going to chat with another member of our team in just a second. But if you're just tuning in, we are announcing the winners of NASA's Lunar Recycle Challenge today. This challenge aims to help astronauts make the most out of non metabolic, recyclable items while on long duration missions to the moon, Mars, and beyond. I'm joined now by Jera Mater, the program executive for NASA's Prizes, Challenges, and Crowdsourcing program, which manages NASA Centennial Challenges as part of the agency's Space Technology Mission Directorate. Jera, thank you for being here.
Oh, thank you so much, Savannah. It is such a pleasure to be here today with University of Alabama and all of you. We're so excited to reveal the winners of phase one and to essentially prepare us for the next phase of the competition. It's great to be here.
Absolutely. Thank you so much for taking time. Now, I understand your experiences in competition and prizes, but this is your first Centennial Challenge in this role. And for us, the first Centennial Challenge that's featured digital twins. Can you give us a brief overview of what a digital twin is and what you saw from our participants in this track?
Yeah, absolutely, Savannah. So a digital twin is a high-tech virtual model that mirrors a real-world behavior of a physical system. So digital twins can use data, physics, and domain expertise to simulate how it performs, reacts, and evolves over time. And at NASA, we use digital twins to help us with a lot of things, to help predict outcomes when experimenting. And this saves us time and resources while we're making strategic decisions going forward. And in this competition, the digital twin track, it invited really a diversity of solvers, the likes of which we haven't seen before in our Centennial Challenges. And we're really, energized by what we saw. And we saw that their submissions gave us a deeper understanding and insight into how they would perform since they have that simulation technology to support their hypotheses. And I believe digital twins have really a tremendous potential to help NASA further its space exploration goals and mission, really in an efficient and strategic way going forward.
Wow, that is so innovative, perfect for our program. And I understand digital twins also had their start at NASA Marshall Space Flight Center with John Vickers. And so fantastic to have subject matter experts like him on the team. I'm ready to hear who won, so go ahead and take it away.
Absolutely. All right. In the digital twin competition track, each earning a monetary prize, the US winners are with Terasynth. Terasynth created the Lunar Reforge system, a compact automated solution that turns food packaging waste into 3D printing feedstock for on-demand manufacturing in space.
And thank you so much for joining me, Jara, and for doing the honors of announcing those prizes.
Thanks, Savannah. It was my privilege.
Welcome. This is a Lunar Reforge system, a compact automated solution designed for recycling common packaging waste within the confines of a future lunar habitat. As required, the system fits entirely within the volume of 4 standard ISS Express double lockers. This compact design maximizes usable habitat space, essential for long-duration missions. Removing the service panels reveals the core components. Currently, the system is idle. The reactor temperature is at ambient 20 degrees Celsius. Energy consumed is 0, and no feedstock has been collected. The cycle begins by processing a standard drink pouch. It enters the shredder, reducing it to consistently sized particles. The control panel now shows the system is processing input with minimal energy consumed, around 0.05 kilowatt hours. Material then moves through magnetic and eddy current separators. Aluminum flakes from the pouch layers are removed here for potential separate use. The panel updates status to separating materials. Energy usage climbs slightly to 0.07 kilowatt hours. The prepared plastic feedstock is fed into the sealed pyrolysis reactor. The system now heats the reactor to the target temperature of 550 degrees Celsius. Energy consumption rises significantly during this phase, reaching 0.5 kilowatt hours. At temperature, pyrolysis begins. The plastic thermally decomposes into vapors and solid char in the oxygen-free environment. Vapors flow into the condensation train, where they cool and liquefy into usable hydrocarbon feedstock. The panel shows pyrolysis active condensing temperature holding at 550 degrees. The energy consumed rises steadily at 0.70 kilowatt hours, and the feedstock collection level increases towards our target yield of 75%. Once the reaction is complete, the system cools. The final liquid feedstock yield is collected. The panel updates to cycle complete cooling. Reactor temperature drops back towards ambient. Energy use stabilizes around 0.72 kilowatt hours. This recovered feedstock is now processed into filament and fed into the integrated 3D printer, enabling on-demand manufacturing. The panel status updates to printing object. Energy consumption increases slightly again, and the feedstock level begins to decrease as it's utilized. This completes one full cycle. From a single drink pouch, 75% usable feedstock was recovered, consuming only 0.72 kilowatt hours in the primary processing cycle. This allows for the creation of essential tools and containers directly on the moon. The Lunar Reforge system, monitored and optimized by its digital twin, offers a compact, efficient, and sustainable path for waste management and resource utilization critical for humanity's future on the moon.